Download this code from codegive.com, link in the description below. OK, let's dive deep into the intricacies of receiving data using sockets in C, addressing potential problems and providing robust code examples. Understanding socket receive, recv, read. The recv, or read for file descriptor-based sockets, function is the core of receiving data across a socket connection. It's fundamentally designed to read data from a connected socket into a buffer you provide. However, there are nuances and potential issues that developers frequently encounter. Basic syntax, recv. *sockfd, this is the socket file descriptor, an integer, representing the active socket connection you want to read from. *buff, a pointer to the buffer, memory location, where the received data will be stored. This is crucial, you must allocate enough memory for the expected data. *len, the maximum number of bytes you want to receive into buff. This limits the amount of data recv will attempt to read in one call. *flags, flags modify the behavior of recv. Some commonly used flags include *message_waitil, instructs recv to block until len bytes are received or an error/disconnection occurs. This can be helpful, but it can also lead to indefinite blocking if the sender never sends the full amount. Use with caution. *message_peek, allows you to peek at the incoming data without actually consuming it from the socket's buffer. Subsequent recv calls will still see this data. *message_don't_wait, sets the socket to non-blocking mode for this specific recv call only. It will return immediately, even if no data is available. If there's no data, it will return -1 and errno will be set to egain or ewould block. *0, the default, blocking behavior. Recv will block until some data is received, a connection is closed, or an error occurs. *return value. *positive value, the number of bytes actually received and written into buff. *0, indicates that the connection has been gracefully closed by the peer, the other side of the socket. This is how you detect a disconnection. *-1, an error occurred. You must check errno to determine the specific error. Common error codes include egain, or ewould block, icon reset, and others. Basic syntax, read. Read is a lower-level function that can read from any file descriptor, including socket file descriptors. The arguments are similar. *fd, the file descriptor, socket file descriptor. *buff, the buffer to receive data into. *count, the maximum number of bytes to read. The return value is the same as recv. Key differences between recv and read *. Recv is specific to sockets and allows flags to modify its behavior, like message_waitil, message_peek, message_don't_wait. Read does not have these flags. *read can be used with any file descriptor, files, pipes, sockets, etc. Recv is exclusively for sockets. In most socket programming contexts, recv is preferred because of its flexibility in handling socket-specific operations. However, read will work for receiving data from a socket. Common problems and solutions. 1. Partial reads, the biggest issue. Problem recv, or read, is not guaranteed to read the exact number of bytes you requested, len or count. It might read less, even if more data is available. This is a crucial point to understand. The underlying TCP protocol is stream-oriented, data is delivered as a stream of bytes, not as discrete packets. Why this happens: network congestion, buffer sizes, the sender's sending pattern, and other factors can cause recv to return with less data than requested. Solution implement a loop to repeatedly call recv until you have received the desired amount of data or the connection is closed. Explanation of receive_all *. One looping *, the while loop continues until we've received the length number of bytes or an error/disconnection occurs. 2 pointer arithmetic * ptr plus bytes_received ensures that we write the incoming data into the correct offset within the buffer. We don't want to overwrite the data we've already received. 3 error handling * the if recv_result == -1 block handles errors. *, if recv is interrupted by a signal, example a user pressing Ctrl+C, we simply try again using continue. *egain or ewood block, this indicates a non-blocking socket, and no data is currently available. You would typically handle this by using select, or poll, to wait for the socket to become readable before calling recv again. This example returns -1 if either of these errors occur. Other errors, for other errors, we print an error message and return -1 to signal a failure. For connection closed *recv_result == 0 signifies a graceful disconnection by the peer. We return 0 to indicate this. 5 success *bytes_received plus equals recv_result, increments the counter of received bytes. Important * in a real client-server application, the receive_all function would be called after the socket has been successfully connected to the server. This example has a placeholder socket call to simulate the socket connection. 2 blocking versus non-blocking sockets. Problem by default, sockets are blocking. This means that recv will wait, block, until at least some data is available or an error occurs. This can lead to your program hanging indefinitely if the sender never sends data or the connection is broken unexpectedly. However, the default blocking behavior is sometimes what you want. Non-blocking solution to avoid blocking, you can set the socket to non-blocking mode. There are 2 main ways to do this. Using FCNTL, POSIX systems. To use this, call set_non-blocking, sockfd, before calling recv. Using set sockfd, cross-platform. This approach is more portable across different operating systems. Handling non-blocking sockets when a socket is non-blocking, recv will return immediately, even if no data is available. In this case, it returns -1, and errno is set to egain, or ewood block on some systems. You must check for this condition. Select, and poll, these are system calls used to monitor file descriptors, including sockets, for readability, writability, and errors. They allow you to wait efficiently for data to become available on a non-blocking socket. The select call predates poll, and is less flexible, but more portable to older POSIX systems. Poll is more flexible, but might not be available on all systems. Example using select, *. Explanation of select, usage *. 1 fd_0, and readfs, clears the file descriptor set. 2 fd_set, sockfd, and readfs, adds the socket file descriptor to the set we're interested in reading from. 3 select, sockfd +1, and readfs, null, null, and timeout, *. Sockfd +1, the highest file descriptor number +1. Select, needs this to know the range of file descriptors to check. And readfs, a pointer to the set of file descriptors we want to monitor for readability, i.e., data being available. Null, null, We're not interested in monitoring for readability or exceptions, so we pass null. Asterisk and timeout, a pointer to a struct timeeval that specifies a timeout period. If no data becomes available on any of the monitored file descriptors within this time, select will return. If you pass null for the timeout, select will block indefinitely. For return value of select, asterisk. *1, an error occurred, check error no. *0, the timeout expired. No data was received. A positive value, the number of file descriptors that are ready, in this case, it should be 1 if sockfd is ready. 5fd_esit, sockfd, and readfds, after select, returns, you need to check which file descriptors are ready. fd_esit, checks if sockfd is still in the readfds set, which means data is available. 3. Handling connection closures. Problem the sender can close the connection at any time. You need to handle this gracefully. Solution recv, or read, returns 0 when the connection has been closed by the peer. This is the standard way to detect a graceful disconnect. 4. Error handling, critical. Problem network programming is inherently prone to errors. You must handle errors robustly. Solution always check the return value of recv, or read, for -1. If an error occurs, check error no to determine the specific problem. Common error codes. EGAIN, or would block non-blocking socket, and no data is available. Can reset, connection reset by peer, the other side closed the connection abruptly. Interrupted by a signal, example Ctrl+C. You may want to retry the recv call. Ibadf, bad file descriptor, invalid socket. Inotcan, socket is not connected. Inomem, out of memory. 5. Buffer overflow. Problem you must ensure that the buffer you provide to recv is large enough to hold the incoming data. If you receive more data than the buffer can hold, you'll get a buffer overflow, leading to unpredictable program behavior and potential security vulnerabilities. Solution allocate enough memory make sure your buffer is large enough to hold the expected data. Use len parameter correctly. The len parameter to recv specifies the maximum number of bytes to read. Null termination, for strings. If you're expecting to receive a string, make sure to null terminate the buffer after receiving data. 6. Message framing, for structured data. Problem TCP is a stream-oriented protocol, so there's no inherent concept of messages. If you're sending structured data, example a series of records, objects, or commands, you need to implement message framing to delineate the boundaries of each message. Solutions common message framing techniques. Fixed length messages. Every message is a fixed size. This is simple but can be inefficient if messages vary greatly in size. Delimiter-based messages. Messages are separated by a special delimiter character, example a new line character \n, a null terminator \0. Length prefixed messages. Each message is preceded by a fixed size field that indicates the length of the message. This is often the most robust approach. Example, length prefixed messages. Sender side *, receiver side *. Explanation of length prefixed messaging *. 1. Sender *. Calculates the length of the message. Converts the length to network byte order using HTNL, host to network long. Network byte order is big-endian. Asterisk sends the length as a fixed size integer, usually 4 bytes. Asterisk sends the message itself. To receiver asterisk. Asterisk receives the fixed size length field. Asterisk converts the length from network byte order to host byte order using antall, network to host long. Asterisk allocates a buffer large enough to hold the message. Asterisk receives the message itself. 7-byte order, NDNS. Asterisk problem asterisk different computers store multi-byte data types, like integers, in different byte orders, NDNS. Network protocols typically use a standard byte order, big-endian. If the sender and receiver have different byte orders, you need to convert between them. Asterisk solution asterisk use the htnl, htns, antall, and entos functions to convert between host byte order and network byte order. Asterisk htnl, host to network long, 32-bit integer. Asterisk htns, host to network short, 16-bit integer. Asterisk antall, network to host long, 32-bit integer. Asterisk entos, network to host short, 16-bit integer. Use these functions when sending or receiving multi-byte data types, example message lengths, port numbers, across the network. Always convert to network byte order before sending and convert back to host byte order after receiving. 8 Security considerations. Asterisk buffer overflows asterisk as mentioned earlier, buffer overflows are a major security risk. Always validate the size of the incoming data and ensure that your buffers are large enough. Asterisk denial of service. DOS a malicious client could send large amounts of data to overwhelm your server. Implement rate limiting and resource management to prevent DOS attacks. Asterisk data validation asterisk validate the data you receive to prevent injection attacks, example SQL injection, command injection. Sanitize user input. Asterisk encryption asterisk for sensitive data, use encryption, example TLS/SSL, to protect the data in transit. Example, comprehensive server/client with error handling. This example combines several of the concepts discussed above. To compile and run. 1. Compile asterisk. 2. Run, in separate terminals. Key improvements in the comprehensive example asterisk. Asterisk clear error messages asterisk per error, provides descriptive error messages based on the value of error. Asterisk socket closure asterisk the socket is properly closed when an error occurs to prevent resource leaks. Asterisk basic connection handling asterisk the server accepts a single connection and then exits. For a real server, you would typically use a loop, and potentially threads or processes, to handle multiple connections concurrently. Asterisk inet_ten, asterisk the client uses inet_ten, for address conversion, which is more modern and secure than inet_address. Asterisk buffer size asterisk the example shows how to define buffer_size to avoid magic numbers in the code. Further considerations. Asterisk threads/processes asterisk for handling multiple concurrent connections, consider using threads or processes. Asterisk asynchronous I/O asterisk techniques like epoll, Linux, and I/O completion ports, Windows, can provide high-performance asynchronous I/O for handling many connections efficiently. Asterisk libraries asterisk consider using libraries like libvent or libov, which provide cross